Hello, my name is Aisling Piggott and I am a PhD student at the University of Colorado Boulder. Today I will be discussing my paper, Deep Q Learning for Aggregator Price Design. As part of this project, my co-authors and I developed the DRAG library for Pythonic representation of home energy management systems. These home energy management systems utilize model predictive control with mixed integer programming to select optimal actions for their HVAC and water heaters in order to reduce the operational cost. The discrete action space given by mixed integer programming represents home energy management systems with minimum run times. For example, a system with a 15-minute minimum on time would be able to select between 0, 25, 50, and 100% duty cycles. The HEMs use R1C1 models of the building thermal envelope and water heaters with noisy predictions of environmental weather conditions and hot water draws to make these decisions. Their decisions are made independently of any other home in the system and made based only on the current and predicted future cost of electricity. The final power consumption of each home is then broadcast back to a centralized aggregator. The DRAG GYM library interfaces with DRAG via Redis to provide a reinforcement learning agent to select the best real-time price per kilowatt hour to broadcast to the community. I would like to emphasize that the RL agent aggregator has no knowledge of home state values other than the sum total of the community's demand and cannot change the homeowner's optimization formula. The homeowner will always pick the operational schedule that will, to the best of their knowledge, reduce their cost. Reinforcement learning works by fitting a multidimensional regression, in this case a neural network, to predict the reward achieved by selecting an action in any given state. In this case, the reward is given as a function of total demand, and the state values include environmental conditions that might predict HVAC usage and time of day data that might predict hot water usage. Reinforcement learning requires no previous knowledge of how the environment works and is adaptable to changing environments. For example, developing communities or the introduction of different home energy management optimization frameworks. The results of this study show that the RL agent designs a price signal that pretty much inverts the time of use price signal used by Excel. The RL agent price signal is smooth and peaks during the evenings when solar power is not being produced. Here, the dashed green line represents the RL price signal, and the dotted green line represents Excel's time of use price signal. The yellow overlay indicates the global horizontal irradiance. We can validate the response of the homeowner to the new price signal by inspecting the home indoor air temperature, given in blue, and hot water temperature, given in red, which in all three scenarios floats between a predefined deadband. The RL agent is effective in reducing sharp peaks in demand that are introduced by the stepped time of use price signal and overall smoothing the demand profile even from a baseline constant case. Here, the dashed blue line represents the scenario under the RL aggregator, and the dotted blue line represents the demand under the time of use price signal, while the solid blue line represents a scenario with constant pricing. In the lower graph, we can see that the daily maximum demand is reduced for most of the days of the simulation, and the overall maximum demand on day 2 is reduced significantly. The combination of these two results shows that the need for ramping and overall grid capacity is reduced. In conclusion, we have introduced a distributed computing network for R1C1 thermal models and home energy management systems. We have shown a reduction of the overall grid capacity necessary in the simulation and a significant reduction of ramping capacity. In one 2007 study entitled The Power of 5%, a 5% reduction in peak demand was estimated to save the U.S. $3 billion annually through a combination of reducing strain on transmission and distribution networks, as well as reducing the need for peaker plant capacity. This study is just a stepping stone, though. The real success of RL agents is in their ability to be transferred to new environments. This RL agent could be applied to either real-world scenarios or larger-scale simulations with more complex home energy management systems. In either case, we predict that the learning period would be reduced significantly with a pre-trained agent. The use of more complex environments or more complex goals is a future area of development for this project. All of the code presented in this project is available on GitHub at github.com/apiggott/drag and github.com/apiggott/draggym. Thank you.